the composition is very easy to prepare, as I mentioned. You take natural transformations, you take composition, all you need to ask what's the component of this composition, and you just by definition say that this is the composition of the components of the natural transformation. And of course, you can immediately check that it follows that the corresponding diagram of the composition is still continuous. So finally, for any functor, there is the identity natural transformation, so there are two possible variations. So that's a natural transformation of the functor itself, and of course, in this session, natural transformation and look at the corresponding component. This is by definition as the identity map. Well, it's useful to have notation for the category functors and natural transformations. So let me just say that for fixed categories C and D, so we just choose any two categories and fix them, we can define the category of functors and natural transformations. The category. So there are several notations. We can write something like we can see so this is category of functors. Another notation which is probably most standard in the maximum category theory. You just write C and D in the brackets. But I hope that you will write the classes, and that's here this is just all functors of category C and category D. So in this category, this one, or even third notation is analogous to the set theory. So the objects are functors, right? From C to D, and the morphisms of functors are natural transformations. So essentially what we define here is that we have this notion of natural transformation, which makes sense for all the compositions, there is the identity. It's enough to say that we have a category of this kind. And another representation would be something like natural between the functors F and G. And so these are all natural transformations between functors, but this is precisely the same thing as the concept, not exactly concept, which is say point space in this category. So the reason why I'm doing this is that when you start this category with some natural constructions, like consider the three category functors, and we look at the point spaces, well, there are no reason to expect that this thing is actually a set. Right? So unless this first argument is a small category, and we can not use for a set, it's not necessarily a set. So this is not really a category, this will be for example, as a category. So there are some theoretical issues here. So it's not a set unless so let's look at some examples. So in these examples, I don't want to check that actually have a natural transformation, so that I have this in the diagram. But all of them literally this is an exercise. And then this exercise will be more similar. So examples But at least we can recognize several constructions that we already know from the algebra, for example. That we can interpret this as natural transformations. And in this hierarchy, we have categories, functors, and natural transformations. Natural transformations is probably the most important. So, for example, if you look at the Martin's book, he wrote that he introduced category theory for the reason to study natural transformations of categories and functors. So, the first example. So, here I consider the identity functor and a natural transformation to the organization functor. So, this is so we have category groups. So in this case, C is the same as D, and this is just category groups. Here, this is the stability, and this is the organization functor. And first, between those functors, there is natural transformation. It just means that from the G, you always have a canonical method. Without the application of the organization functor. So it's not hard to check that this is actually. So if you want that this arrow that I have here, this is the average. You can look at this as the complement notation for the natural transformation. They always say theta as a definition, and this is theta summation. So this is one of the natural transformations. Now, in the second example, so let's change the code. Right, so then we have the duality functor D from the category of vector spaces over K to the category of vector spaces over K. And what this thing is doing is just taking a vector space and raise the whole space of the let's say the dual space, the star, which is all over 3 from the vector space, and you can see the space of all vectors or one point over. So, you see the state. There's something that needs to be checked very quickly. So, usually the duality functor is a contravariant functor. So, this is a functor from the opposite category. If you want to consider covariant functors, and we do this course, but we want to consider contravariant functors. Yeah, so for example, if you have two finite dimensional spaces, what's this functor is doing for the map into finite dimensional spaces? Say the map is given by dimensions. So what's the deal with this dimensions? Yeah, so this is just the two maps. This is just composition dimensions. Okay, so this is the functor. And now the natural transformation of that is the following. Again, notice the diagram. All this is needed on the standpoint of the diagram. So we have again the same category vector spaces, and we have two functors. So one functor is the identity functor, and another functor is the D squared. Or maybe the Laplace D, the Laplace D. So now notice if you have a contravariant functor, then it's quite expressed with the covariant functor. So here I don't need to write it. So it works without help. And there's a natural transformation theta. And the natural transformation theta in this case, so say theta component of the vector space D, this is just the harmonical map from the vector space and the harmonical from the vector space or forms
on the dual vector space, and each vector you can interpret as a form. You just compute this vector on a form by evaluating the form on the vector. So this is a natural transformation. So example 3. Maybe a little bit more interesting. So we're going to learn what it is a determinant. So the category, let's say that we have category of commutative rings. Well, we can generalize this slightly for non-commutative situation, but it's much harder. To the category of groups. Now there is many canonical functors from the category of commutative rings to groups, but one of the simplest is probably just GLN. Right, so you take the invertible n by n matrices with the coefficients in the given commutative ring here, let's say ring R, and the special case is just the GL1. Or in other words, you just take all invertible elements in the commutative ring. This is the same thing as the GL1. And we have a natural transformation between these functors, and as you probably guessed, the natural transformation is called the determinant. So you can interpret determinant as natural transformation of two functors on the category of commutative rings to the category of groups. Okay, maybe another example from commutative algebra. So now let R be a commutative ring and S inside R a multiplicatively closed subset. So then in this case you have localization of modules and have the following situation. Take modules over R, again modules over R, and two functors. The first one is the identity, and the second one is the localization at the S. And there is also a natural transformation because you have a canonical map from the module to the localization of this module at any multiplicative system S. So that's another example. Okay, so in this list of examples, for examples, we consider a situation where we kind of look at individual natural transformation, but we can also try to understand what happens if we take the whole category of functors and natural transformations. So, for example, 5. Let C be a category, any category that you like, and I is a set. By the way, I forget to mention this on the first lecture, any set is also a category in a natural way. You just take this set and consider this set to be a set of objects, and you don't have any arrows. Well, you're supposed to have identities, so you add these identities for any object, but no other arrows. So this is a discrete category. But it won't be important in this example. So let's take a category and the set. So can you tell me the answer to the following category? C to the I. Here, interpret this I as a discrete category. I already know that I can define this category. Well, it was D to the C, but doesn't matter. So the category of all functors and natural transformations. So what it is in this case? Now you can just look at the definition, right? You're supposed to, objects, well, at least we can understand the objects, right? All objects are just functors. But how you can specify a functor from a discrete category to a category? And so that you don't need to do anything on the arrows, right? Because there are no arrows in the I. So essentially you take every object in the I and you associate an object in the C, right? That's the functor. But if you just think about this for a minute, you realize that this is precisely the product of several copies of the category C, well, as many copies in the set I. Okay. Example 6, maybe a little bit more interesting. Well, I want to say that G is a group, but the only reason to do this is just I'm hoping that you're more familiar with the groups than monoids. I can as well say that, say I have M, a monoid, so is a group. So then G is a category with one object, as we discussed last time, and I can look at the following. I take the category of all sets. Well, maybe if I want to consider this as a category, I'm going to write G underlined. So what is this category of functors and natural transformations from the G to the sets?
Please may I repeat what is written in this 6 point?
Well, I'm saying that I have G, which is a group. Then I can interpret a group as a category with one object, with additional property that every arrow in this category is invertible. Right, so I just take, I have this one object, remember that was as before, in the category G underlined, the objects is just some element that I'm going to call star, right? And then you have homes from star to star, and I'm saying that this is by definition the given group G. So, yeah, so the answer for this is precisely G sets. Maybe let's spend several minutes to understand why this is G sets. So, as I mentioned, in the category G underlined, there is only one object, and if you want to specify a functor, so you have a functor f from the G to the sets, right? To specify a functor, you need to say where objects in this category are going to as an object in this category. But since you have only one object, it's very easy. So this object star goes to some set X, right? I suppose any set that you can choose, right? But then we know that we also have a map on the home sets. It means that the G, which we can identify with the home from star to star, well, this is just by definition, this is supposed to be mapped to the homes. Well, and I need to apply the functor to this star, and we agree that the application of this functor to the star is just some set X. Right? But this is precisely the map that takes element G and sends this to the bijection, I don't know what it's supposed to call, sigma maybe, sigma sub G from X to X. Bijection. But this is one of the definitions of the action of the group G on the set X. Right? So the fact that this functor sends compositions to compositions means that this action is associative, and the fact that this functor sends identity to the identity, well, it means that the identity acts as the identity transformation on the set X. So indeed, this looks like a G sets. Well, I have another example of, actually I have two examples. So one is kind of more almost the same, so I'm going to just write an answer. So 7. You can take the category of vector spaces over K, and consider all functors again from the group G to this category of vector spaces. And if you just repeat this argument, you can identify this with the category of the representations of G over this given field K. Yeah, and probably the last example that I want to show is the following. Now, it's kind of like example 5, but I want to take a little bit more interesting category. So let's take the category I to be, by definition, the category with 2 objects and 2 parallel arrows. So this is the category I. And the question is, if I take sets to the I, well, maybe since this is a category, according to my notation, I'm supposed to underline this, but for the I usually don't do this. So what's this category? If you use analogy with these previous 3 examples, can you guess the answer? Right, again, to specify a functor, what you're supposed to do, you have now 2 objects, right? You need to associate a set here and a set here and 2 maps. What the mathematical structure it is if you have 2 sets and 2 maps?
Product of 2 categories sets.
No, not exactly. For the product, you need discrete category I. And here, this is not discrete. I have 2 additional. Of course, I don't write this, but I also have the identity. So if I call this object A, I call this object B. Of course, there is 1 sub A, and there is also 1 sub B. And that just this information is always there, so I don't write this on the blackboard. But the additional information is these 2 parallel arrows. So what kind of mathematical structure could be specified by 2 sets and 2 maps? No, this is a graph, right? So you have the set of arrows, you have the set of vertices, and for each arrow you associate the beginning of the arrow and the end of the arrow. So this is the category of graphs, directed graphs.
So can you explain it again? The example again.
Yeah, so I was saying that this functor, if you apply this functor, you get the following. You have the, say, set A map and set V. This is the data you need to specify if you want to specify a functor, right? So functor takes an object, and when you apply this functor to an object, you get an object now in the sets. So this is supposed to be a set. I'm going to call this I, A, and there is another object I'm going to call, when I apply a functor to this object, V. So if you wish, if you say that you have functor F here, right, then this A is the F of the little a, and this V is the F of the little b. Right? And then you also have 2 arrows, so this arrows by a functor maps to another arrows. So this is the data that you have in the category of sets. But you can interpret this data by saying that this is a graph. Because if you want to specify a graph, you need to specify the set of arrows, you need to specify the set of vertices, and for each arrow you need to associate the beginning and the end of this arrow. So this is what 2 maps are doing. Now it's kind of weird way to define graphs from a point of view of category theory. Okay, so I want to finish examples of natural transformations, and of course essentially you can see that up to this point this is more or less terminology, but essentially the rest of the course is just using this terminology and proving some theorems with this terminology. So, and before I start proving something, I need probably the last definition, an equivalence of categories. So categories C and D are called equivalent well, you can compare this with the definition of isomorphic categories. So they are equivalent if there are functors again, I'm going to write this on the same diagram, F from C to D and G going in the other direction. But now, additionally with these 2 functors, I have 2 natural transformations. So if there are functors and natural transformations, I'm going to call them alpha and beta. So let's say alpha is a natural transformation. Well, not just, let me correct this immediately. And natural isomorphism of functors. Natural isomorphism of functors. So alpha is from the composition of the G and F to the identity on the category C. So this is natural isomorphism, and also there is natural isomorphism beta for composition in the other order, F and G. Okay, so in this case, notation is the following. So denote equivalent categories as C, now equivalent to D. So for the isomorphism, I would use a different symbol so we can write the following. So if the category C is isomorphic to the category D, so this is isomorphism, then immediately this implies that the categories are equivalent and the reason why I'm writing this stupid sentence is so you can see what's the difference in the notation. This is for isomorphism and this is for equivalence. So as you can guess, because we have these two weaker conditions, they're not just equal as functors, but there is some natural transformation that make them kind of equivalent. You have a lot more examples of equivalent categories than you have of isomorphic categories. And this is the right categorical notion when you want to consider two categories to be the same. Well, an example, silly example, kind of constructed by hand. Of two categories which are equivalent but not isomorphic is the following. One category has only one object, let me call this A, and there is only one arrow, one sum A, so discrete category which is just a set with one object. And another category which is equivalent to it but not isomorphic, equivalent but not isomorphic. It has two objects, X and Y. Of course you have two identities for two objects, and you have two additional maps, F and F inverse, meaning that in this category X and Y are two isomorphic objects, but two different objects. So then these two categories are equivalent, but of course they are not isomorphic. They are not isomorphic, for example, there is no bijection on the set of objects. But the equivalence, I think, is easy to see, right? You can in one direction, you can define a functor that takes this object and, for example, sends this to the object X or Y, doesn't matter, but let's suppose it goes to the X. And in the other direction, the functor takes X and Y, of course, to the object A. So that will be functor G. And you can check that, of course, in one direction, this will be just the identity, but in the other direction, if you come first, go here and then go back, then you get as the natural transformation, which will be exactly, has component F and F inverse. No, F in one direction, F inverse in the other direction. Okay. So the first goal, the first theorem that I want to show is that we can say that the two categories are equivalent if there is a functor between those categories which is essentially surjective and fully faithful. This is our first important theorem. We're going to prove this in steps, and the first step is a lemma. So I want to formulate this as an independent lemma so I can use this later. So the lemma is actually quite natural and almost trivial if you think about this. So if F is a functor from the category C to the category D. So if F is a functor, this is what we're given, And yeah, I'm also going to use D naught to be a subcategory, full subcategory of the category D. So for any full subcategory, of course, I have a canonically associated functor which just embed this full subcategory into the category. Okay, so this is the data satisfying requirement, so such that for any object X in the category C, there is object Y in the category D naught and an isomorphism of the f of X and Y. So essentially I'm saying that up to some isomorphism, the image of this functor f is in the subcategory D naught. This is what the assumption is saying, without formulas in terms of words. So then there is a functor f naught from the category C, the category D naught, and isomorphism of functors so theta naught from the functor f to the composition of the I and f naught. So moreover, if theta 1 is another such isomorphism between f and the composition with some functor f1, so is another isomorphism so then there is unique natural transformation theta from the f1, well again not just natural transformation but the natural isomorphism of the functors f1 and f0, and you can say that the theta 0 is the composition of I and theta 1. So you can factor this to the subcategory D naught, and you can factor this essentially in a unique way. Okay, so proof. So by the axiom of choice for any object X in the category C, we can choose Y in the D naught and fix also isomorphism phi sub X from the Y to the f of X. Clearly we can do this if you have this assumption of the lemma and apply the axiom of choice. And now I can define this functor f naught by using these choices. So we set f naught on the object X to be by definition object Y that we choose, and for the arrows, so if f is a map from X to the X prime, so in the category C, then we set f naught on this map F to be, well, this is supposed to be a map from the f naught applied to X to the f naught applied to the X prime, but we define this as the following composition. So set this as the following composition. From f naught of X, you use isomorphism phi sub X and go to the f of X. then here you already know, since we're given a functor, that there is a map from the f of x to the f of x prime. And then finally, the map actually goes in the other direction, but since this map is an isomorphism, this is not a problem. So there is phi x prime. So this goes from the f naught of the x prime. So if you look at this composition, again, this last arrow in the wrong direction, but this is again an isomorphism, so not important. So we can go on there using fx prime inverse. So if you look at this composition, that's precisely the arrow that we want to get. This will be from f naught of x to the f naught of x prime. And clearly from this definition you can see that the identity is mapped to the identity. So the only thing we need to check is that the composition goes to the composition. And this follows from the following diagram. We have f of x. So suppose we have two maps, f and g. So this is to the f of the x prime. So I know that I have this property that the composition goes to the composition for the functor f. So here, if you want more details, f is a map from the x to the x prime, and g is a map from the x prime to the x double prime. Now this we can identify using phi sub x with the y, which is in this case as we using this as to be f naught of the x. Now here we have y prime, which is f naught of the x prime, and the map is f naught of the little f here, so this is the same thing, x prime. Okay, so this is the diagram that we have. And if you look at this diagram, since you know that the composition for f goes to the composition, the same is true for the f naught. And moreover part I'm going to leave as an exercise. Since everything is so simple, I think you can do this. So that's the end of this proof. Now from this lemma, I want to derive another lemma about the skeleton of the category. Maybe I put it here. So lemma so for any category C, there is a full subcategory which I'm going to denote as K of the C, and this is the skeleton of C. So there is a full subcategory skeleton of C. There is an embedding I from the skeleton of C to the C. So I is an equivalence of categories. And the skeleton has an additional property that in skeleton two isomorphic objects are equal. So that's the definition of a skeleton. And from the proof you can see how we can immediately construct this. Again, I'm using axiom of choice. As the axiom of choice, choose one object in each isomorphism class of the category C. And let the skeleton of this category to be the full subcategory consisting of these objects. So it's very easy construction. For each isomorphism class, we just choose one object and consider the corresponding full subcategory. And this will be a skeleton, and it satisfies, well, clearly it satisfies the second property, right? So the only thing we need to check is that there is an equivalence of categories. So up to an equivalence of categories, each category looks like the category with this additional property. Okay, so we can use previous lemma to conclude that the identity functor on the category C, right? We can write this identity functor as the composition of two functors, the embedding I composed with the functor F naught. So this tells us that if you consider these two functors, one is I and the other is F naught, right? So then the composition is the identity in one direction. So the problem is to show that if you take composition of the F naught and I, you still get the something which is naturally isomorphic to the identity functor. Well, that's a following computation. You look at the composition of the I, F, and again I. So first put parentheses around F and I, right? So then this is naturally isomorphic to I, F, I, if you put parentheses in the other order. But now this first composition is, of course, as we already know, the identity. If you take composition with the identity, this is still I, right? And then this I we can rewrite as the precomposition with the identity on the skeleton, right? So now we have this composition of three functors and that composition of the two functors which are the same. So clearly you can drop this I from the equation and write that the composition of F and I is the same as the identity on the skeleton of the category C. I'm forgetting to write notes everywhere, right? So the question is why we can drop this I from this formula. Can you explain me why this last line follows from the previous line? Clearly, you cannot do this just for any functor, right? For example, some stupid functor that sends almost everything to one object. But in this case, you can do this. Remember that I was by definition the embedding of the skeleton of the category into the category. So what is the property of I that we can use? Well, I haven't defined the notion of a monomorphism for the functors, and I'm not going to use this. But at least you know that this I is fully faithful, right? For functor I is fully faithful. And if the functor is fully faithful, you can drop this from this identity. So this works since I is fully faithful, right? If this is fully faithful, it means that on the Holmes, this doesn't, well, this give you a bijection, but if you have a natural transformation between these two functors, right, it means that before you apply this functor I, you get some bijection between these two functors. So hence we have this, and this proves that we have equivalence of categories. In one order this is identity on C, in the other order this is identity on the skeleton of C. Okay, so finally let's prove the main theorem of today's lecture. So sometimes people write this as a formula, so equivalence of categories is the same thing as the essentially surjective plus fully faithful. So let's call this as a name of the theorem. And the statement more precisely is the following. A functor f from the category C to the category D is an equivalence of categories if and only if f is fully faithful and essentially surjective. Okay, so this is if and only if statement, and in one direction this is trivial, right? So if you know that this is an equivalence of categories, of course this is essentially surjective and fully faithful. So in one direction this is clear. So the non-trivial proof is contained in the other direction. And here we can look at the diagram. So we can take the skeleton of the category C and take the skeleton of the category D. So here I have the embedding, so let me call now this I sub C, and there is a functor going into the other direction which gives me an equivalence of categories. I want to call this functor J sub C. And the same for D. There is an embedding I sub D and functor going in the other direction J sub D, which gives an equivalence between the category and its skeleton. So here between category C and D there is functor F, and finally here I want to consider composition of the J sub D, F and I sub C. So that we have the, if I go using functor F, I can as well go just using the corresponding functor here. So I'm claiming that the composition of the J sub D, functor F, and the I sub C is an isomorphism of categories. Right? So this is the first claim in this direction. Well, the isomorphism of categories, well, this follows just because we have this assumption that this is a fully faithful functor, right? So this is bijection of the Holmes sets, and this is essentially surjective. So if I go to the skeleton, it will be a bijection of the objects in the skeleton of the category. So this is an isomorphism of categories. So if this is an isomorphism, there is a functor, let me call this functor K, which is inverse. So there is functor K, which is its inverse. So then the I sub C, K and J sub D is quasi-inverse of f, which you can check immediately by taking the composition. So the only thing I haven't defined here is the quasi-inverse, and probably should have done this when I gave a definition. So the quasi-inverse is in the situation of the equivalence of two categories. If you have functor f and there is functor g in that direction, this g is called quasi-inverse. So, sorry, I forgot about this definition. But you kind of construct this immediately by using functor k in this situation. Okay. So I have only a few minutes left, so maybe I look at the several examples. Again, something from the algebra that you already know about the equivalence of categories. So, for example, you can look at the category of the right modules, and this is equivalent to the category of the left modules, but over the opposite ring. So one equivalence of categories that you know very well from the algebra. And the second example of this kind would be something like this. You take bimodules of a given non-commutative ring R, and you can identify the category of the bimodules with the category of the modules, say left modules, but it's not really important. You can as well take right modules. So left modules over the R, then the product with the R opposite. And the third example that I think we're going to do this on a seminar at some point, that we can take, say, let's take for simplicity. Well, okay, so let's take no, not important. Left modules, and you can identify these left modules with the n by n matrices over R, and again left modules over this matrix ring. So remember that I asked the question, is it true, for example, if you have two equivalent categories of modules for two different rings, is it true that those rings are isomorphic? Now in general it's not true, and here is a counterexample. There's even a counterexample in the case of a field. For example, the category of vector space is equivalent to the category of modules over the ring of n by n matrices for any n. So this is probably not immediately clear. I think these first two examples are easy if you know definitions. These are just trivial statements, but this is an interesting statement that requires some proof. So exercise for the seminar. Okay, so I think we're out of time, so let's take a break.
Доводилась такая категория, мы должны иметь морфизмы между любыми объектами. Эта категория, почему они существуют? Такая категория всегда между любыми двумя функторами может.
начинать? So I remember that last time we finished with some topological questions, but I think before we do these topological questions, let's discuss one general question. I think it's not very hard. I think it's easier than these topological questions, but still useful. So let C be a concrete category show the following two general observations. So first one is that any surjection is epi, and of course the corresponding statement for the injections. So any injection is mono. So since a lot of our examples are examples of concrete categories, almost all of them are concrete categories, so it's useful to know this just general property and just use it, and not to show every time when you try to show that, for example, epi is the same as surjection in one direction. This is automatic.
May I ask, we are using the definition of computer category from previous lecture.
Yes. In fact, this definition of a concrete category, after the second lecture, it has potential to generalizations. So you can say that that the category is concrete with respect to some other category if there is a fully faithful functor from this given category to this other category. In this sense, what we call concrete category is just concrete category over sets. So I have a plan to create a Google class for this class. And for example, I'm going to use it to upload some problems. So essentially this will be problems from the seminars, but maybe additional problems that we don't have time to do on the seminars. And you can use this as a preparation for the quizzes. So if you want access to this Google class, just send me an email and I'll add you to the Google class and you will see this PDF with the problems.
sets category.
Well, can you explain why these two things are equivalent?
So there was a definition by we have like C concrete. If objects in C as sets with structure,
Mm-hmm.
and morphism are maps of sets preserved with structure.
Mm-hmm.
So I think it's clear that if C concrete in definition with structures, where is faithful functor, we just
Maybe you just write this.
yeah
Give a name to this functor.
When we take functor that sends some object x objects of C underlined is like sets with some structure on a set. So we just take set on which this structure is constructed and send this set to set. Like,
Yeah, so getting the structure.
yes.
Mm-hmm.
And morphisms like we send some morphism.
Well, I suggest you just write S as for the structure for shortness.
Yeah.
Mm-hmm.
We send with morphism just to map so why it is faithful, we need just to check that on morphism it is injective. Like distinct morphisms goes to distinct images of morphisms. So I want to show like what if there's two maps of sets like this one, like f from x to and with when with way inverse images are distant, like by the definition definition of injection.
Yeah, but this is just a
Oh,
definition.
no, like I want to prove not, A implies B, but B, not B implies not A. Okay, like if we have F and we are distinct, I want to show that with morphism as a maps are distinct, but because this in concrete category with this maps preserving structure, if they are distinct, they should be different as a maps because they preserve structure. So if there are two distant morphisms in our concrete category and we use this functor on these two distant morphisms, we'll get two different maps. So it is faithful functor because of preserving structure.
Okay. How you want to derive from this definition these two statements?
I guess.
Well, you can erase another blackboard from the lecture.
Yes. So we wanna show the underlined concrete. It wanna show that suggestion is an appears. So we have some F. And we know that map between sets are surjection. So what I want to do, it's like we have this composition and this composition. I want to take functor from category to sets. So take this. Was equal to, because F is functor. It's equal to this, because with just two equal morphisms is equal to this. So we get equality of like this equality. And in categorical sets, we know that surjection is appearing, so we can kill with morphisms and get like.
Yeah, you can erase this. Yes.
So replace that. Okay. So we know that. But we know that our functor is faithful, so it implies,
Mm-hmm.
And for injection at mono, I guess the proof is similar, but we are just inverse.
Yeah, so the proof, the computation is the same, but just the order is different, yes.
Можно просто еще раз сказать, почему можно про структуру забыть? Почему Facebook?
So, на русском можно. Ну, в смысле, мы просто отображаем объект, ну, у нас в конкретной категории объекты — это множество со структурой. Мы забываем структуру, и нам нужно доказать, что и как бы морфизмы, которые приводят множество структуры в множество структуры, мы просто как бы приводим буквально в отображение множеств. И нам нужно просто показать, что для двух разных морфизмов в нашей конкретной категории у нас это разное отображение, как буквально отображение множеств. Но это так, потому что у нас отображение сохраняет структуру. Если они разные, они должны отличаться как отображение на множестве.
Yeah, I think this works. So yeah, so I'm going to formulate another problem. Maybe we don't do this problem just for do this for the as a practice for the first quiz, for example. So the problem is, again, C as before is a concrete category. And then if F is a retraction, then this implies that F is surjection, and if F is section, then F is injection. So one more property of the concrete categories. So this is something that you can think about at home, and I suggest now we go back to these topological questions and finish these topological questions. So the category that we consider C is the category of topological spaces. Now I believe that the last time we discussed the situation that the monomorphisms in this category are the same as injective maps, and we finished this part, right? If I remember correctly. I think you gave a proof, yeah. Yeah, and today we're going to finish this problem and also show that, well, maybe I don't need to underline this, show that epimorphisms are precisely the same things as the surjections. So you can we finish the proof? Yeah. So.
Do you know what talk is concrete? Like.
Yeah, it's clear.
So this is done. So we need to prove in.
No, since this is concrete, and we know that every surjective is epi.
So epi is surjective.
Mm-hmm.
So we want some topological space. We want to show some not surjective. Not surjective and not epimorphism. So I think we should get two-pointed set with anti-discrete topology and show.
I suggest that you write this. The topology is anti-discrete. I mean, just a word.
And
Because in the first proof, it was important that the two-pointed set that you consider is discrete topology, right? Now you're
Yes.
taking anti-discrete topology.
and we want to construct some morphism that's not surjective and not happy. So I think we should get the image of A and B by.
Yeah, I don't quite understand why you need these two maps G1 and G2. Why you need these two maps G1 and G2? I think you want to consider just a map F from A to B, right? Yeah, and then do something with this map. Like consider its image.
So B, like this B, I wanna to show it and A. So all A goes to some F. So then, and in second stage, we can. I think we just need to to send Fauzi to is one point A small a G2 of B is small point B. Like where A is not opened, so we don't care about NS image of A. It can be anything because A is not open subset and B is not an open subset, so we don't care about.
Yeah, but the maps that you consider just sends everything to a point. I think it's clear that these two maps are continuous maps, and this is not a problem.
Yes.
But are those maps useful? This is my question. Now, for example, you need something like the composition of the F with G1 is the same as composition of F with G2, right? But is it really true? I don't think so.
With I think one of this map isn't useful. So and our map can send image of A and B to A and our to B, like G2. Send F points from image of A and B to A, a small, and B our way. So
I'm pretty sure this is not how you're supposed to write this. So probably what you want to write is that you want to define the map G2, right? Say, for example, on the point X, right? So then this is A, right? If X is in the image,
Yes, I want
and this
to
is B, if this is not the case. So essentially what you're trying to say is that G2 is the characteristic function of the image of the map F.
Yes. So, and we can see that with equality takes place, but with functions are different. So f isn't happy and isn't subjective.
No, this last sentence, it's kind of weird. You have this, right? So you have that these two compositions are equal. This is clear.
Yes, and
So you know that, suppose that this is epi, right? We want to show that any epi is a surjection. Let's suppose that f is epi. Then you can cancel this G1, you can cancel this f, right? So G1 is equal to G2,
yes.
meaning that the constant function is the same as the characteristic function of the image. It is possible if and only if the image is the whole space. So the map is surjective.
Yes, I think yes.
Okay, thank you. Anyway, so you need to write your name and two check marks that it solved the problems. Okay, so before we continue, was it clear how we solve this? Okay, so let's do one more topological example.
Я должен поставить галочку?
Ну, за две задачи, вот за вот эту и за две. Okay, so I don't know the standard notation, so let me introduce notation. Let house stands for the Hausdorff topological spaces. So let be the category Hausdorff topological spaces. Now, as you can see, the proof that we have here, or we had last week, that the monomorphism as the same thing as injective maps works in this category too. So there are no differences. So mono is the same thing as injective maps with the same proof. But you can notice that here, well, of course we know this is again the concrete category, subcategory of the top. So of course we know implication in the other direction by this general problem that we solved in the beginning of the seminar. So, but you can see that the proof that the epimorphism is surjective that we use here doesn't work in the category of Hausdorff spaces, because, for example, this space is not Hausdorff. But what you can show is that epimorphisms are precisely the same map as dominant maps. The same thing as dominant maps. Dominant. So recall that f from x to y is called dominant if the image, you take the image of this map, take a closure, and this is equal to the space y. So in this category, we have more epimorphisms than we have surjective maps. Of course, any surjective map is dominant, but there are other non-surjective dominant maps, like embedding of rational numbers into real numbers. Yes.
Yes, and we know this equality epimorphism is equal to surjective, right?
Yes. In the category of all topological spaces.
Then it should be true for the category, right?
No.
No?
No. And this will be a counterexample.
Okay.
No, you need to prove this statement that epimorphism is precisely the same thing as a dominant map in the category of. Hmm?
In Hausdorff category.
Yeah, in the category of Hausdorff topological spaces. Yes. If you want to talk about counterexamples, for example, you can take rational numbers embedded into real numbers. That's a dominant map in this category, and this will be another example of a epimorphism which is not surjective. So, but here we need to prove a general statement. No, you need to show two directions, right? One direction I think is quite easy. If you know that the map is dominant, show that this is epimorphism is not very hard. The hard direction is the other one. How to derive from the epimorphisms that the map is dominant. So try to do, for example, just first direction, and then maybe I'll wait another 5 minutes, 10 minutes, and give you a hint for the other direction.
I may go in one direction.
Okay.
May clear.
Sure. No, let's clear this completely. It's from the previous problem.
I want to group from dominant to epimorphism. Let's take 3 topological spaces, Hausdorff topological spaces. Let my dominant map be F. Here we have 2 different maps, G1 and G2. We have something like most of the space is an image of F, and this is the difference. Y without f of x. This is exactly what is f closure of x minus f of x. We know that if we want to prove that it is epimorphism, we should look at G1 composition F is equal to G2 composition F, and we want to prove from here that G1 is equal to G2. Let's suppose that they are not equal, then there should be some point y from exactly this place, because we know that here they should be equal. You may say it clearly like now. Y cannot lie in this part because for this part we know exactly that this is surjective map on f of x, and that means exactly that we can write that G1 is equal G2 on this place. Now for this, what does this mean that G1 is not equal G2? That means that we have 2 different points. This is G1 of y, this is G2 of y. Since it is Hausdorff space, we may obtain 2 not intersected vicinities of these 2 points. Thus, we should take pre-image. I want to make it bigger. Thus, we have this point y and 2 vicinities, 2 pre-images of those 2 vicinities. Since the intersection of 2 vicinities is again an open set, this is the pre-image of this one is open through G1 because it is continuous map. Pre-image of this one is continuous, is open through this continuous map. Thus, this is 2 open sets in Y space. We may intersect them, obtain in U open set, and this open set contain our point Y. Y lies in the here. What this mean? What does this mean? This means that for every vicinity of point Y, we should contain some points from f of x. For example, this point y stroke. And for y stroke, we know that
images of Y stroke by G1 and G2 are equal, but those two vicinities have empty intersection.
Yeah, I think it makes sense. And I also need to write your name and check mark. Yeah, so this gives a proof in one direction that dominant is epimorphism. Yeah. Maybe for the other direction, let me give you a hint, because I think if you don't know this hint, it might be quite a difficult problem. So we're trying to show that epi implies dominant, right? And essentially, what you want to show, you want to kind of, as in the previous proofs, you want to find nice maps G1 and G2, right? Such that the cancellation give you the result. So in this case, you can do the following. Let us before say that we have topological spaces A and B, continuous map F. So this is Hausdorff topological spaces. Let's denote K to be the image. So then you can consider another space, maybe we call it C, and you take a copy of B, you take another copy of B, and glue them together along K. So this is gluing together two copies of B. Is it clear what I mean by this? You take, the picture will be terrible because, well, I can't really draw something that is dense, but say this is a copy of B, and you take another copy of B and you glue them together, so this part, which is K, is precisely the same. And outside K, they're different, because for different points in the K, you're supposed to get different points in this gluing construction. Now, for this C, we definitely have two maps, G1 and G2, right, which you can just embed into the C this B by two different ways. You can embed this as a first component, kind of component, and the second component. So try to apply definition of an epimorphism. Well, first of all, if to use this construction, the first thing you need to show is that the C that you obtain this way is again Hausdorff topological space. It's not clear from the definition. So this is something you need to verify, and then just look at these two maps and the compositions. Another proof that doesn't use this. Okay, let's see this.
Maybe you can check it if I'm wrong. Let F be epi and consider space of 4 points with topology A, C, B, C, A, D, and Z.
So these are all open subsets, right?
Yes, and you can see that it is Hausdorff.
Well, you can check this, right? You can consider all pairs of points and find neighborhoods.
Yeah.
Okay, suppose we believe you that this is Hausdorff, okay?
Sorry. B and B prime.
Sorry, what's B prime? So we have 5 points.
We need 5 points. And now
May I ask, tau is topology or base for topology?
it is. Oh. Yeah, oh. Sorry. Forget.
Okay.
Okay, I'll start with proof of the fact that the space B disjunct union with B quotient by F. Let's say that we have space A, B, here would be okay, let we have two spaces at first, A, B, map F. Let's suppose that map F is non-dominant. That would mean that the closure of f of A in B is not the B itself. So
let's just write this, what we're trying to show. You assume that the map is not dominant, right? Is this the right symbol?
This is from the first.
Yeah, but if you add not dominant and we want to show this is not epimorphism, that's precisely what we're trying to do, right?
А в прошлый раз я разве не доказывал, что если доминант, то эпиморфизм?
Yeah, you did. But we're trying to show that epimorphism is dominant, right?
Сейчас нужно доказать, что
Yeah, you want to show this.
yes.
So you're assuming
I
that this is not dominant and you want to
Yes.
show this is not epimorphism.
Yes.
So this is what I'm trying to write here.
Right.
I'm just asking, is this the right logical symbol for the not?
Right. That's it. Okay. First of all, I need to say that this is Hausdorff space. How to do it? We should know how to separate every 2 points in this space. I have 3 different positions of these points. Let's call this copy of B with index 1 and this copy of B with index 2, that we can separate them. First of all, first point is in B1 an image of B1 without f of A in this space, and the second one is in this image. That's easy in this case. We can take as a vicinities that those spaces itself, because this is a closed space and this is a closed space, thus those 2 spaces are open, and in this space they are represented by the classes that contain only 1 point, and pre-image of those classes should be exactly the same. So they should be open and everything is okay. The next case, we have x1 in the same copy as x2. In this situation, we should also take, first of all, this open space and then find 2 separate vicinities of x1 and x2 in space B1, because we know that B1 is Hausdorff. Let's name them U1 of x and of x, U of x1 and U of x2. Those are 2 separate in B1. Thus we should obtain the vicinity for the first point to intersect this subset with this one. Those 2 open, then the result is open too. And take this one, intersect with this one, and we will obtain the resulting open space that separate those 2 points. Third situation, when x1 is in this copy is in one of copies, and x2 in the image of closure of f of 1 or f of a. In this case, we should find two non-intersecting vicinities in B1, for example. For points x1 and x2, those exist because of Hausdorff's, because of the fact that B1 was Hausdorff. In this case, if use this picture, we have one point here, one point here. We have two, let's forget about the right part, we have two non-intersecting vicinities. And if we talk about pre-image of those two, then the pre-image of this one is obvious. Pre-image of this one separates in the situation when the vicinity intersects with the copy of the B2. Here B2, here B1. But if we take pre-image, it should be open again because of the definition of our quotient space. And the last point is situation with x1, x2 in the image of closure of f1. Here is also the similar situation. We should take two non-intersecting vicinities of those 2 points in one of the copies, then map them to the image of the quotient space. When we take pre-image, the same situation as here happens. And thus, we see all of the cases, all of possible cases for positioning of 2 points. And we see that we obtain two non-intersecting vicinities in every case. Thus, this space is Hausdorff. And the final idea, what we should do, may I clear this?
Sure, sure.
That's very simple. We should choose G1 as an identity from B to the first copy, and G2 as an identity to the second copy. Thus we see that those two are not equal, but the composition is equal because they give the same answer for the space G1 restricted to F closure of A is equal G2 restricted to F closure of A.
Okay, thank you. Yeah, so also related question, but I think among these topological questions, maybe this implication that we just proved was the hardest. I think the next question is easier, so we're not going to discuss this on the seminar, but this is a problem that, for example, I can give you on the first quiz. And the problem is the following. So let C Hausdorff be the category of compact Hausdorff spaces. So in this category, you can show again that this is even smaller, right? So the Hausdorff spaces for the full subcategory of all topological spaces. This compact Hausdorff spaces is the full subcategory of the Hausdorff topological spaces. Now in this smaller category, monomorphisms are the same thing as the injective maps, and epimorphisms are again, as in the top, the same thing as the surjective maps. Okay, so this is an additional exercise. Well, maybe we can discuss something algebraic, not topological. What if we just to finish this topic about epimorphisms, monomorphisms, what if we take the category to be the category, say, of the left R modules, right? Is it true that monomorphisms are the same thing as the injective maps? Is it true that epimorphisms is the same thing as the surjective maps?
Like linear space.
Hmm?
The maps are linear maps.
Yeah, sure. Yeah. So in the category of R modules, the objects are R modules and the maps are R linear. Actually, I think this algebraic question is much easier than the topological questions that we discussed.
May I ask, is it true that for compact Hausdorff spaces, every dominant map is surjective?
Yeah, you essentially solve the problem.
А почему нельзя брать примеры, как из прошлого семинара, то есть, то есть брать модуль как кольцо над самим собой и брать контрпримеры для коммерции для таких случаев?
Ну, у нас там были,
Нет, ну это просто другой категории пример будет. Там, если у вас два кольца, там были гоморфизмы колец. А здесь у нас должны быть гоморфизмы модуля над фиксированным кольцом.
Если рассмотреть как кольцо над самим собой.
Ну, хорошо. Но все равно отображение это будет отображение модулей. Если рассмотреть отображение из кольца в кольцо, да, отображение из кольца в кольцо как отображение модулей, это просто само кольцо. Ну, это, грубо говоря, надо просто понять, куда единичка переходит. А отображение колец, ну, это группа автоморфизм, да. Ну, как-то эндоморфизма кольца, это, в общем, что-то такой другой объект. Sorry, what's commutative?
R is commutative.
Arrow? What arrow?
Like ring is commutative.
No, in general, no. Not necessarily. Okay, it looks like we have only a couple of minutes left, and it's not enough to present the solution of this problem. So maybe we stop here and continue with this problem next week. And I also have another question, easy question, but kind of interesting that you can think about. If you have a functor between two categories, is it true that the image of a functor is a subcategory? Just something to think about. Okay, so let's finish for today and continue next week.